Hi. Good morning, everyone. Welcome to the last day of the summer school. So today we have Adèle Ribeiro, our speaker for this morning. She currently works on the Philips University of Marburg and is now in the way to move to University of Münster. Yeah. So she works in Causality. She previously worked with Elias Bernbaum. It's a difficult name to pronounce. And well, let's welcome our speaker.
Yes. So thank you so much for the introduction, for the organizers for inviting me here again. It's really a pleasure to be in this school. I will talk about causal inference. Of course, this is a huge topic and it's getting bigger and bigger every year. I will try to cover the basics. So the most important part for me is to motivate you to be in this field because I really believe that's one of the missing link in AI. So let's get started. So I always try to make a comparison between predictive models and explainable or causal models. And to understand this, let's try to see some papers related to each of these tasks. So we are used to see AI for diagnosis or predicting diseases. So we have, for example, AI systems that are better than human doctors at predicting breast cancer, for example. But on the other side, we don't have a way to understand how these models are getting the outcome, how the outcome is coming about. So we miss this part of explainability. At the same time, we don't have a way of making sure that the algorithms and the systems are being fair according to the standards, the fair to be fair according to the standards in our society. For example, in natural language processing, we have these large language models like ChatGPT that has impressive abilities. So you all know here, for example, they are all usually all predictive tasks. You can get so brainstorm ideas, explain, like create AR art, write a resume. So basically, it's repeating patterns that you observe in the data. However, for like mathematical problems, even like a classic answer engine outsmarts AI chatbots. So why that is this mismatch, right? So these algorithms cannot reason. And one of the missing link for this is causality, in my opinion. It's one of them. Of course, we have many big challenges in AI, but the ability to understand causal and effect relationships is crucial to understanding and to have this deeper understanding and to make decisions about the processes. So that's the biggest challenge here that we are going to talk about. How can we make this? What exactly is missing, and why there is this lack of understanding in AI systems? So we have this mathematical framework of causal data science, and it was popular, it became very popular in 1995, around 2000, with Yuda Pro. Yuda Pro, he wrote this book, Causality. The first edition was around 2001, and this is the second edition. I would say that's a reference book for everyone that's working in causality. And he's a director of the Cognitive Systems Laboratory at the University of California, UCLA. And he won the Turing Award. That's the highest distinction in computer science for exactly the contributions to artificial intelligence through this development of calculus for probabilistic and causal reasoning. It's about causality. And he has this very nice, so this is from the Book of Why. I took this quote from the Book of Why. Is also is a really interesting book if you are trying to understand why causality is important. And he has this sentence, so deep learning has instead given us machines with truly impressive abilities, but no intelligence. So there's this distinction about ability and intelligence. And the difference is profound and lies in the absence of a model of reality. So I want to stress here model of reality, because this is what actually is missing, the connection with the reality. Of course, causality was haven't started with Perot. It started way before in economics. So we have these three researchers. So Joshua Angrist is a professor of economics in MIT. Together with Guido Imbens and Donald Rubin, they are professors of economics and statistics, and they wrote also books related to causality, especially in economics and biomedical sciences. And they also won the Nobel Prize because of their contributions to causality. So as I said, this is 2021, and as I said, everyone is recognizing the importance of causality for AI. Even Yoshua Bengio, a few years ago, he also started working on causality. Everyone knows him, right? So he wrote the deep learning book. He's a professor at the University of Montreal, and also the founder and scientific director of Mila. And he also won the Turing Award because of the deep learning, right? But recently he started also working on causality. And this is a quote from his interview saying that causality is very important for the next steps of progress of machine learning. I don't know if I can give you more reasons to see that causality is becoming really popular, and a lot of these big names in AI are recognizing this is an important missing link for especially reasoning. So just summarizing, this is my view of why causality is important. So causality allows us first of all to identify causal effects. And causal effect can, everyone knows that the effect can be derived from randomized experiments. However, here we are looking at the same outcome. We want to determine the effect of an intervention. So if you change the road, you want to know what would happen after this intervention. And here we don't really need to perform the intervention. We want the same goal, but the idea is to determine the effect of this intervention even if you don't perform the experiment. So it's an unrealized intervention. And this is different from observing a statistical association, right? So we want to distinguish here between associations and causation. So the difference between just observing two events being correlated or statistically associated, to the fact that if you perform an intervention or if you change the value of a variable, you want to see what comes after. And this is related to direction. You have the notion of directionality and the idea of cause and effect relationships. So that's the first idea. Everyone, I think, can get the goal of the importance of causality for identification of effects. The second one is explainability. Why explainability? Because we usually want to understand the underlying mechanisms, and the underlying mechanisms is related to causality. We believe that it exists a causal model that generates the data, and understanding these mechanisms allows you to have full explainability, basically. If you have the full causal model, you have full explainability. Understanding these mechanisms are usually through something that we call causal discovery. And we will talk a little bit about this. But once you have explainability or understand these mechanisms, you can assess fairness, for example. It's just a particular case of disentangling how these mechanisms are performing or predicting an outcome. Generalizability. So how can we have, like once you identify the effect in one domain, can I just assume that it's going to work in a different domain? Of course, there are some assumptions that you have to do to make this work. And understanding these assumptions and getting the unbiased effect in these different domains is something that's dealt inside of the field that's called transportability of causal effects. And the last one is data fusion. So many people are working using the language of causality to combine these different data sets that we have. So and not necessarily just data sets, but also prior knowledge. So we need to combine all these I would say assumptions, or like all the mechanisms that you can, how can you combine all this knowledge that you have that are coming from multiple and heterogeneous studies? Can be like from experimental studies, observational studies, can be from just common sense in our society. So how can you have this encoded in a formal way, and then we use this knowledge to then expand the model. So all those topics are, I won't talk about all these topics in this lecture, but they are covered. So if you are interested in any of these topics specifically, you can come to me. I can give you more pointers later. I will try in this lecture to cover the first two topics, causal effect identification. I won't have much time to talk about estimation, but I can explain how this works a little bit, and then causal discovery. If you are just starting in the field, I would recommend you to start with this book. It's a very short book. It doesn't cover much, but I would say that's for like a first introduction, it's very good. The intention of this book is, so it's by Pro and Madeline Glimmer and also Nicholas Jewell. They created this, they wrote this book especially to give a course in statistics. So if you are interested in causality, I would start with this. Then there are also a website that was created by the Elias Weirenbaum group that while you are reading the book, you can basically create these graphs and play with several tools inside of this web page to understand the exercises inside of this model. And I mentioned already the Book of Why. If you haven't read or haven't, I would say that this is it's not technical, right? So many people believe that the theory is inside of this. This is not. This is just a way to motivate people to come inside, to come to the field. But it's a novel, I would say. Like, it's a very nice book to read before you go to sleep, like just to have fun. But don't believe that the theory is just there, right? You need to look for more advanced books. I would say that's more technical. And Causality, this is the reference book for everyone. To be honest, I would say that just reading these books is not sufficient. These are outdated already because the field is advancing so fast that, and we don't have books to cover what we have right now. So basically everything that has been developed recently are still in scientific papers, but those are like very good books to understand the topics, because those challenges are still unsolved. Like, everyone that starts reading this book are going to see the importance of every topic there, and then you go after the scientific papers to know about what has been developed. But through the lecture, I will also provide some references for these papers that I believe that are the breakthroughs in causality. Okay, so I want to now give you a task, a very simple task, just to motivate the difference again between prediction and reasoning. So imagine that I have here this. So this is the task. Can I guess the size of a fire by observing the number of firefighters? It's easy. I'm just asking you to guess. So imagine that you look at the window. There's like 100 of firefighters out there. Can you just guess what's the size of the fire? Small, big? You can guess, obviously, right? So it's a big fire. And how I do it? So I just need two variables. I have the number of firefighters in action, and I want to predict the size of the fire. I can, for example, have any, I can use any technique. Here's just a regression model, and I have a very good fit. So I have an R square of 92% and a positive correlation. What kind of tells me that the number of firefighters is a good predictor for Y. So the fact that there is a correlation automatically gives me this the result that the variable that I'm using is a good predictor for the outcome that I'm interested in. Okay. And so this is the definition of correlation. So the fact that I have a variable X, in this case is the number of firefighters, that the probability of Y, once you observe this variable X, is now different than just observing Y, right? So this is X, the information of X is helping me to have to predict something better about the variable Y. And this distribution, everyone knows this. This is called in the field observational probability distribution. So we are going to have a distinction here, just the name observational, because this is just coming from an observation. Y and X are observed variables, and I can obtain, for example, the conditional probability of Y given X, the marginal probability of Y, and I can see that those are different. Once these are different, X is a good predictor. And as I said, there's this positive correlation, which means that the more firefighters, the stronger the fire. Simple like this. But humans are very interesting creatures. They look at a correlation, they look at a link, and they automatically want to make decisions about this. So someone can say, oh, great. So there is a positive correlation, which means that if I have, so the greater the number, the number of firefighters, the higher is the bigger is the size of the fire. At the same time, if I reduce the number of firefighters, I expect that I also decrease the size of the fire. So you want to make an action. Once you observe a correlation, automatically want to make this action and say, okay, let's use this as a policy, right? And what do you think? Is this going to work or not? Why we are laughing? Why we know that this is not going to work? Can someone here give me just a reason? Why is this the case? No, they are not independent. You just observe a correlation, a positive correlation. They are highly correlated. It's not. There's a very high correlation. How do you know there is no causation in which direction? Exactly. You have prior knowledge to know that the number of firefighters depends on the size of the fire, not the other way around. And this is like knowledge about the underlying reality. Like that's what Pro was talking about in that sentence. You need a model of reality to reason about the reality, right? And so it's not sufficient to just observe a statistical association. Can be the highest correlation that you can ever get, can be like 100, like a correlation of 1. And this is not sufficient to tell that this is a relevant variable for intervention. Here you can guess. guess is something different than predicting effects of intervention. So here, it's a misleading correlation. So the size of the fire that determines the number of firefighters needed, right? Not the other way around. And the causal direction is determined by understanding the underlying reality, as I said. So we need this model. So this model can be completely unknown, but I need to know that X is a function of Y. So X here is the number of firefighters, and Y is the size of the fire, right? So X is a function of Y here, and Y is, I mean, there are other factors affecting the size of the fire, which are those captured through these other variables U, but those are not X. Those doesn't include X. It's the other way around. And knowing this, so from this, like this functional relationship, we define what is a cause. So if X is not if Y is not a function of X, which means that X is not an argument of the function of Y, X is not a cause of Y. Because that's exactly what we are expecting. By changing the variable of X, if it was an argument, we would see a difference in the outcome Y. But if we don't have this as an argument of the function, it doesn't matter. I won't change the value of Y, right? So changing the number of firefighters through an action or an intervention, and in the field we have this notation do. It's just a hypothetical intervention, doesn't need to be an experiment. I'm just imagining that I will have a way to change the variable of X, and this is just a notation, mathematical notation. So changing the number of firefighters through this do X won't affect the initial size of the fire. This is pretty obvious, but if you move the scenario and I just see correlations out there, I'm seeing that if I drink a lot of coffee, then I'll probably have like a stroke because of a correlation. But this doesn't mean anything. What are the other possibilities for spurious associations or misleading correlations? Who here can tell me? This is a case of just reverse causation, right? So we were imagining that there was a causation, that Y was causing, that X was causing Y, but not the other way around. But what else can happen here to create associations that are completely spurious without it? That's the way to say it. Who here have heard about other reasons? Exactly, can be just, if you have another variable that's affecting or being, for example, if this UX and this UY have like a shared variable and they are affecting both X and Y, this is going to create some other association that's completely unrelated to causality. X is not causing Y, Y is not causing X, and there's a third variable that's called confounder in the field that would create also an association. So there are many things that can happen here, and we are going to try to formalize all these concepts through this lecture. So I will start from the beginning, from what is a structural causal model. Of course, if you have access to this model, you would have full explainability because it's the model that actually generates your data, okay? So this is just the base of the entire field. So even the field is sometimes called the structural framework of causality. And it's because of this idea that there exists a structural causal model that generates your data. So the structural causal model is just a tuple. We have like 4 elements in the tuple. The first one is a set of variables V. We are always going to call it V. V are those variables that you actually observed. So you have a data set, the columns of your data set are your variables. Those are the variables V. Of course, those are not only the variables that exist in the world, and your phenomenon can actually be explained by variables that you never got the chance to observe. Those are going to be the variables in the set U. Okay, the first one is sometimes called endogenous, but it's just the set of observed variables. The second is called exogenous variables because it's outside of the observed system. And we have also a set of functions, and we are now interested in determining the functions that explain the variables in the set V. So a variable in the set V, which is an observed variable, is a function that the first parameter is PA because it's from parents. In graphical models, we are going to see what are parents, but those parents is a subset of the set of observed variables, right? So the first argument here are the causes of the variable Vi that are observed. Of course, we also have other causes that are not observed, and they are in the set of exogenous variables U. And the last one is the probability of these exogenous variables. Together with an assumption, which is the fact that we are going to say that this model is recursive, which means that there's no way to have like a cycle. For example, if I start with a variable V1, it cannot depend on any variable. Then you have a second variable, it can only depend on V1. And then the third variable can depend on the second and the first, and so on. So there is a recursive way of determining each variable. We will see that several researchers are now relaxing this assumption, but the field started with this specification of a model. And this model is already very powerful. If you are from statistics, for example, probably you have heard about this structural equation model. And the structural equation model is a very particular case of a structural causal model. But when you look at this, suppose that I ask you, write a structural equation model and then estimates the parameters. What actually you have to do? You have to first determine what are the variables that I have available. I have to guess the order because I have to write the equations. So I have to guess that X has only here an intercept and some error terms. X can depend on Z, but not Y. So I'm creating, like I'm forcing this causal direction in this sense because I'm inducing some order. Also, if you see here, they are all linear functions. The arrow terms, they usually are independent of each other. Like this is the covariance matrix. So I'm not only writing when I write this model, I have several assumptions, and those assumptions are usually just because I need to estimate the parameters. I have to identify the parameters. Otherwise, I don't have identifiability. It's an underdetermined system. So you can see here that while I write this, I have to specify the causal order. I have to specify the parametric form of the functions. What are the distributions of the variables? This idea that the arrow terms are all independent of each other, this means that I have no other variable that can actually create associations between two observed variables other than just the observed variables, which is something that we call causal sufficiency in the field. Or in other words, I'm just saying that I observed everything relevant for the system. Then basically once I have everything all the parametric and distributional assumptions, I can estimate the parameters. If everything that's written here is correct, I have a causal model. And the parameters here, they are the causal effects, right? The effect, for example, of Z on X is just determined by this beta XZ. But why we don't call this causal? We could. And the idea behind it are in the assumptions. If those assumptions are correct, everything is fine. Everything is causal. But we want to relax. And this is what the field is trying to do. That's the major goal of the causal inference field, is to relax the assumptions in the sense that I will have then a higher probability of getting the right model and explaining the model of reality. Because there is this connection right now. I can assume and I can estimate, and I have a number in the end. But is this really modeling reality? That's the reflection that we have to do. So let me formalize a little bit more. So this is the structural causal model, suppose that I have, right? So let's start with this idea that I have written, I'm not writing here F, because in the structural causal model, you don't need to specify right now the functions. I'm just asking that exists a function. And let's look only on the arguments of these functions. So here in this simple example, just have two variables, x and y. And y is a function of x, but there is also this shared component, which we already discussed here, that can also create associations. So if I from this model, if I get the distribution of it, so we call it observational distribution. And we can use, if we find that the probability of y given x is different than the probability of y, or that x and y are statistically dependent, we are able to predict the value of y after observing the x. That's the task we just saw. And this is going to happen, this correlation is going to happen by just having one of the situations. Like I just need that either x is a cause of y or both, right? I have like some shared component that are both like argument of both functions. This is sufficient to create associations. But if you are interested on the effect of an intervention, we are interested in a different model, which may not be the model of the reality, but it's a model that you manipulated and you fixed the variable x to be a constant, because this is what an intervention does, right? You go in the nature, you change the nature, and you say x is no longer depending on all the other variables that are in the row. We are going to fix it. I'm giving you a drug, for example, to you. What is the effect of taking this drug? So I know that x is fixed. This is called hard intervention. And then if in this model, we call it mx here because I change x. So I mean, this is the manipulated structural causal model or interventional structural causal model. If we get the distribution that's induced by this model, we call it now interventional distribution, which is related to intervention on x, right? So it's dependent on the variable. And now it's denoted differently because it's no longer this probability of v, or where v are the set of observed variables, but it's a probability after changing x. You did something differently, right? And this probability can be different from in the left side. And if in that model, we have now that the probability of y is different than the probability that you observed here, is because you actually have a cause, that x is actually influencing something. Because there you changed, here you didn't change. If both are the same, this means that changing doesn't matter. But if you have a difference, it's because actually is having an impact on the probability of y. And that's why we can get causal effects from experimental studies. If you run, you see this a little bit better later, but that's why if I perform a randomized control trial, for example, and then I see a difference between the control group and the case group, is because X is a cause, right? We are comparing two different, so the case where X is not being manipulated and the X where you have the X being a placebo, for example, or X being a drug. And if you see a difference, you see that that has to be due to the variable X or the treatment variable. Questions about this?
In that case, I don't need to invalidate all the causes.
You don't need to?
Invalidate all the causes.
What do you mean by invalidate? Here we have the model, and if I manipulate the model,
All the causes change. You just telling us that in that case, if the last one changed, we are sure that it was due to the first one.
yes, but you could have other causes. This is just this is like a model specific for X. Obviously, you could have other variables affecting Y, as I have here. But this is just telling you if X is affecting Y or not. Okay. Okay, let's move on. If I don't have the model now, I have, for example, access to what is induced by this model. What is induced by this model can be just observational data, can be the distribution that you can estimate from the observational data, but usually this is just induced by a model. And we could also have knowledge of order and the existence of confounders. And this model here, we are going to see how it's constructed, but we are going to define it as a causal diagram, is just explaining the, is a qualitative explanation of the model where you just represent the directions and the existence of confounders or not, right? So I'm not telling here what are the functions that that exists behind the variables, but I know by looking at this graph that Y is a function of X and some variables that are affecting both. We will see later. But you could have this from prior knowledge. I know what is the order of, for example, in the example of the number of firefighters and the size of the fire, I know that X here is the fire, Y is the number of firefighters, and not the other way around. I could also have other variables affecting both, politics maybe, but there are, and then I cannot remove this edge if I don't have the knowledge that there's only those variables affecting the system. And from the left side here, we only have the induced object. We also have in the right side the induced object. So the interventional data is this data that's coming from a manipulated model, for example, a randomized control trial. And the distribution is called interventional distribution. And the difference in the graph is that since, if, for example, I'm randomizing all the confounders that could affect X and Y, usually you don't, this X is fixed, right? So here in the equation, X is fixed to a small constant, this is small X is just a constant. So I have no variable pointing into X because X is fixed. When you have a randomized control trial, we try to mimic this situation where all the confounders are randomized, so you don't have any variable influencing X anymore. So this is the representation of an interventional world, which may not exist, but can be just hypothetical in the sense that I haven't performed the intervention, but that would be the representation. And if I have the graph, I can just manipulate the graph and reason about what would happen after an intervention. And so here is just what I just told you about the randomized experiments. Everyone accepts that the randomized experiments can access this interventional distribution, this probability of Y given to X. But remember that you only have unbiased estimate if this is like a perfectly realized randomized experiment, right? So if you have biases, you also don't have the causal effect. But that's what happens. Like you have a pair of variables that you imagine that X is affecting Y, and there are like a lot of other variables that are affecting both, and I cannot control, I cannot observe. But I can either control or randomize. And if I separate into two groups, you see that if the expectation of Y coming from the first group, which, for example, can be a placebo, is different than the probability of Y given another value for X, for example, the treatment. If those two groups are different, this difference is going to be different than zero, and then that exists a causal effect. And then that edge in red between X and Y is not zero, so that exists a causal effect. So that's the idea, and you see that we are only looking at one edge of the entire system, but you can control and randomize the confounders, which are, I would say, the most challenging part of causality, to get the clean effect if it exists from X to Y. But we have this question, and what if we cannot conduct randomized experiments? There are many situations that this is just unethical. For example, cancer. Can you randomize patients with cancer? I can give cancer to this person. I cannot, right? So, or practical limitations. Sometimes you need to wait years to see the effect. Smoking, for example, was one of this case. Or logistical, or can be just expensive. What do you think we can do in this situation? Can someone here give me an idea? We are here looking, we are trying to estimate the model of reality. And this is connected to large language models, right? We are here trying to learn the model that we use as humans to speak or to write. This is a model of reality. What are you doing to learn this model? Sorry? No, any case. You have if you have a case where you cannot perform randomized experiments, or you don't want to because it's expensive, what are you doing to go after this true model or this model of reality? Collecting data? What else? Yeah. You will see what's the impact of just having data. That's what's happened. Suppose that this is my model. That's the true generating model that we are after it, right? So we are trying to estimate this model. And suppose that I don't have the knowledge, so it's in red there because it's shaded because I don't know, right? So this model induces a causal diagram. It's just a representation, the graphical representation of the model, right? So it's always a one-to-one representation from a true model. Sorry, one model has only one representation for the causal diagram. And this causal diagram then induces, or the model itself induces some data. That's what you have in the end. Suppose that I then, and then I can, sorry, the animation is a bit faster than I wanted. And then from this data, you can, for example, run a very large deep neural network with billions of parameters, and I have like a very good estimation of this probability of y given x. Okay, this is what we are doing, right? We get the data, we don't look what's happening there, and we estimate here this probability of y given x because we are looking at a predictive task. So this is working. But I told you that many models, by just changing the type of function, by changing the distribution of the U variables, right? We have a different set of exogenous variables. You can do so many things there and you still induce the same causal diagram, right? So there is a problem here where many models induce the same causal diagram. And there is this result that this causal diagram here, which is a representation of conditional dependencies and independencies, we will see this later, induces the same constraints in the data, right? So there are many models. They are different. You can have different functions. We are respecting the order. So even with the order, we have like different models that are inducing the same order and the same existence, the same constraints related to the confounders. But when you go to the data, these constraints are also the same. And there are many models with it. You can also change the order, the models, which are going to have a different order. Now, y is affecting x. So y is a parameter for the function of x. And the same constraints are going to have there in the same data set. And you have multiple models with different explanations, structural explanations, where the same constraints are there in this data, which is the constraint that x and y are correlated. If you're looking for correlation, you have this no identifiable problem of, I don't know which model generated my data. And this is sufficient to predict the task, even like perfectly, if you have like the most expressive, like if you have the most powerful machine learning model to have like the possibility to estimate or to infer any type of functions. You can have the best model here, but you are still just looking at correlations to do a predictive task. You are not looking at the model there. And that's a conclusion. And you look here for this two, in the end, there is no bidirected edge, which means that even in the case that you observed every variable that's necessary to explain the confounder relationships, you still have a non-identifiable problem there, right? So, of course, measuring as many variables you can is good, it is. But there's still this issue that I will never distinguish between these two graphs, or even between these multiple models. Okay, so to go from the left side to the right side, I need to encode knowledge. I need to make more assumptions. So just data, passive data, won't get me to the true causal model, never. I need more assumptions or encode more knowledge. And you can try to explain the model that was fit here to the data. It's going to have some explanations, but this explanation don't necessarily match with the true causal model, with the true model of reality. So you may have like a way to explain your deep neural network, but not necessarily this is explaining the language of humans. Can be just explaining the model that was fit to the data. Okay, that is this mismatch. And we have now pro-causal hierarchy that tried to formalize this notion that we have different types of inferences that we can do. So this is from the book of Why. So the first layer of this ladder of causation is the observational rank, right? It's called associational rank, where we are just interested in conditional probabilities or marginal, but just these probabilities that are coming from this observational distribution. And we can do a lot, right? So we are here, we are experiencing a lot of advances in the side of predictive models. We have like machine learning, could be supervised machine learning, unsupervised machine learning. We have Bayesian networks, decision trees, deep neural networks. They are all very fancy models to predict this observational probability of y given x. They're just tools. If you're just interested in one specific correlation, we have like different ways in statistics, 200 years of people working to understand how you estimate this from data in a really good way. That's what we are doing. But the questions that we can answer with this are like, well, how would seeing X change my belief in Y? This is a guessing problem. What does a symptom tell us about a disease? Again, it's a guessing problem. But if I want to change the type of question and ask what would happen if I change this variable, what will happen with this other variable, is a completely different question. And you need a different probability distribution, which is the interventional probability distribution. And in machine learning, we have tools for that, which is the reinforcement learning, because it's doing a lot of experimentation there. So it's dealing with the interventional data. It's like a lot of randomized control trials that you are doing there, and then in the end you can recover the causal effect. But we are going to see here causal Bayesian networks, which is a different tool that we can also learn the probability of y given do x, right? The interventional probability. And this can give us the answer for a different type of questions. What if I do x? So what would y be if I intervene on x? So there is this action. So will my headache be cured if I take an aspirin? You see an action there. And there's even a third rung of this ladder, which is very complicated. That's the counterfactual layer that's dealing with an even different type of probability, which is the counterfactual probability that deals with different realities. So imagine, for example, that I took an aspirin, and then I can ask, was it the aspirin that stopped my headache? So I already took the aspirin. I don't know what would happen. I cannot go in the past, change, and see what would happen with me. So that's why it's also related to a more personalized effect identification, right? But while you go up in this ladder, you need more and more assumptions. So in the first layer, we just need data. There's a theorem that tells you just data is sufficient. If you have you go to the limit of data, you can have infinite data, you have this answer. But in the second layer, you need more. And that's a theorem that allows us. So the challenge here is to move across this layer. So how can, for example, just use data to go to the second rung and do inferences about causal effects? And that is this theorem that says that the ladder almost never collapses, which means that if I'm interested in the full causal diagram, for example, which is in the second layer of this hierarchy, I cannot identify fully the causal diagram unless I have more assumptions about this. Unless I have experimental data, unless I have parametric assumptions and more. Just data doesn't collapse. It's not sufficient to do inferences in the second layer. And it's the same for the second to the third. You need more and more assumptions about the structural causal model. So just to conclude here, let's see if you are paying attention. So I have this XKCD, and it's really funny, but that is a very interesting thing for us to think about here. So I'm going to read for you, but you can also read. So another huge study found no evidence that cell phones cause cancer. What was the WHO thinking? And then the other guy says, I think they just got backward. Well, take a look. And then you have this plot here. So it is over time. So many people believe that time is going to help you to solve a problem, right? But you can see clearly here. In 1970, there was this increase in the total cancer incidence. And a few years later, 20 years later, it's a lot, but 20 years later, we see a almost perfect correlation also in this trend of cell phone users. And if you just look at this, there is time involved. It really really shows that the total cancer incidence, so the cancer is causing you to use cell phones.
So just for totals, but for the related number of cell phone users and the cancer incidence due to cell phone users.
This may be one issue, but so what else we can?
6 or 10 dots. The totals and also the.
So you believe that there is a causation here? If you change to a relative number?
It says we need to see more data. We need to go into the data of the ones that use telephone and have cancer and the ones that don't use telephone and have cancer.
So who here believe that we'll be able to decide the true relationship, but by just maybe analyzing better the data that we have or collecting more data in this way? Who doesn't believe? Good. So, I mean, when we say data, we need to be more specific, of course, right? Because, as I said, there are different types of data. So just by looking at number of cancer and cell phone users, we can wait 100 years. We can have 1 billion data. I will never get the answer if mobile phone is causing cancer, or is the other way around, or if there's just a third variable causing both. Can be technology, which is what I believe here, but I don't have the answer, right? Technology help us to identify better cancer. At the same time, make the cell phones more accessible to everyone. So at the same time, so technology is really involved here. I don't know if there is a cause, but for sure there is a confounder, which could be that graph. But I don't know, could be this, could be that. And which type of data you would try to get to answer this? That's a question here.
Experimental data?
Yeah. It's unethical, but would solve, right? So yeah, you can try to use different types of data to understand why there is a mismatch happening before technology and after technology, for example. But this is just a proxy for technology. You could try to measure technology, or you could measure more and more confounders up to a point where you have all the variables related to this phenomenon. But you always have this question, am I already done with all possible confounders? It's really hard, right? So maybe you can, maybe you cannot, but definitely observational data won't get you to the answer. So, and it's really funny because this, you see, this is what we believe, that we just spend more time collecting data. That's a matter of hardware, that we just have no power to analyze this data, and this is not sufficient. Let's see how much time I have. I have time. More questions?
Just a couple of considerations. In this specific case, wouldn't be, I mean, if there's a factor that you can measure, and then the increasing of the factor doesn't affect the result, it's like saying that then that factor has not an influence on that. Is what we usually accept as common sense reasoning. So if I am exposed to the sun and then I deliver cancer, I couldn't be in the condition to say that sun causes cancer. But if I'm not exposed to the sun and then I deliver cancer, then I could say that sun is definitely not a cause of cancer. So in the negative sense, it could help us. And also the second question is related to basically this, you could also have part of the data population which is showing X and a part which is not showing X. And that's also the typical way you approach that in biomedicine, isn't it? So basically, I would say if I have half of the population not being exposed to cell phones, and then I have the curve of cancer incidence, I could compare both things just like in an ANOVA analysis. Or isn't that related to the causality inference, partial causality inference at least?
If you don't have cancer, can you really say that you are representative of a population? And because you can have other factors protecting you. It's possible that cell phones cause cancer, although for you, this was not significant enough to give you cancer. But of course, you need to, right? There is another issue here, that this is a statistical problem. But what I'm saying here is that even if you have a coverage of the entire population, and if you are seeing this correlation, just a pair of correlation, if you observe that there exists a correlation, so in your case, it wouldn't exist, right? So you could have no correlation. So no correlation implies no causation. But if you have a correlation, you really don't know if this correlation is due to cause of one variable on another, if it's just other variables affecting, because you cannot rule out this possibility.
Yeah, but if the factor affects everybody, that was my first assumption.
If it affects everybody,
right?
You
the,
still
the increased number of phones, let's assume everyone is going to have a cell phone, because if there's a population not affected by cell phones, not interacting with, then the problem is different.
You still could have like some radiation coming from the sky.
Yeah, of course, you could also have sun. But the question, if you increase the number, the factor that assumably could affect, and there's no effect. You understand? So the factor shouldn't have a cause on that effect. That's what we usually accept as common sense reasoning. So if the number of cell phones is increasing exponentially, let's say, and the number of cases is remaining constant, and that number of cell phones is affecting everybody, so the conclusion could be, might be, or surely not affecting. This factor is not affecting. Of course, you cannot conclude that, let's say, getting out cell phones is going to increase the number of cancer occurrences. That's absurd. But the fact that it does or that it does not affect, it does not affect, because if everybody is exposed and the number of cases doesn't increase, then that factor is not affecting. Because if we don't assume that, how are we going to do factor analysis?
It is counterintuitive. You want that this should be true, but this is not. Like, because you could have alternative reality where this is just showing the as I told you, it could be something external from you, and if you don't observe this, you would never be sure that that's not the reason. We can talk later. It's a hard thing to grasp. Okay, let's move on. I want to connect with Bayesian networks. I want to know first who here have heard about Bayesian networks or studied this in machine learning. Great. And because many times we believe that causality and Bayesian networks is related, but let's see how it's related. So a Bayesian network is just a graph, right? There's no semantics here. And I'm going to present here a definition of Bayesian networks that allows confounders, which I'm going to call, many people that have heard about Bayesian networks saw a representation through a direct acyclic graph or a DAG. I'm going to extend to a cyclic directed mixed graphs just to allow some other confounders that are not observed. But the goal here of Bayesian networks, which is really important for you to know, that the Bayesian networks just represent conditional independencies. That's all. Okay? So that's an encoder of conditional independence. And I'm going to just present a few triplets. Triplets are just three variables connected. So you could have an understanding about an important tool that I'm going to mention later, which is this separation. So imagine that I have this representation. This is a graph. It's just a graph, right? And I have two variables, X and Y, obesity and baldness, that if I look to a population and I have like a sample of it, we will observe that there's this positive correlation. So the more obese you are, the more bald you are, right? And I mean, we know that this is not the case. And why this is not the case? That's one thing. But we have right here a confounder, right? So if you have like a kid that's obese, we don't expect it to be bald. It's just that while we get older and older, we expect that we get more fat, but that's just age there. And there's a confounder, right? So it's a very simple model. Of course, there could have many other things between these variables here, but this is representing an interesting phenomenon that if you observe two variables and you get the marginal correlation between these two variables, obesity and baldness, you can observe some statistical association. But once you condition on a different variable, you may lose. And then you have conditional independence. So in this example, X and Y are independent given Z, right? Simple example. And this is going to be represented by this graph. We will see later how. But this graph is representing these two. That's the important part. This graph represents these two statements that X and Y are correlated or statistical dependent, and X is independent of Y given Z. Let's see another model that's now a chain, because I have like, this was a fork. The second one is a chain. And suppose that diabetes affects the probability of stroke, right? Then I don't know if I have diabetes or not, but maybe I know that my family has a history of diabetes. Because of this history in my family, I have a higher probability of having a stroke. And this is represented by this graph here. And you see that later that it's representing exactly the same two statements, that X and Y, if I don't observe if I have diabetes or not, X and Y are associated, because X is helping to predict the probability of Y. But once you observe that I don't have diabetes, for example, doesn't matter if my family has a history of diabetes or not, my probability of having a stroke, maybe right now, is going to be independent of my history. This is, again, a very simplistic model. But it's representing something that's important to note here, is that's representing exactly the same set of conditional dependencies and independencies, right? There is another one that's this is structure that is like pointing to a variable z, forming a V. So sometimes we call it V structure, or in the case Z is a collider in the triplet X, Z, and Y. We have a descendant of W. So graphical models, we have this notion of family relationships of children and parents and descendants, ancestors, and so on. And in this graph, let's think about it. Imagine that I have two variables, diet and physical activity. Suppose that they are completely unrelated, okay? It's not, it is a simplistic model. And if I just get like data from what's the type of diet you're having, the quality of diet you have, and the amount of exercises you're doing, you have like this independence, okay? Let's suppose that this is independent. But imagine the situation that I know that the person is doing a lot of exercise, a lot, like it's an athlete, but it's obese. Can you guess what's the type of diet of this person? It's a very simplistic model, okay? Probably it's a disease and so on, but let's assume that it's just diet and physical activity affecting obesity. You would say that this person is eating very poorly, right? And this is the case that X and Y were independent. So you got just data, X and Y, they were independent. Now you condition on a third variable and you create association. Because now the fact that once I observe that the person is obese, I have a high correlation between exercise and diet. And this is inducing a spurious association. And this is very dangerous because depending on the set of covariates that you are adding to our regression or to your model, this can create associations even for independent variables. So sometimes you can even think, oh, this is a good predictor. Yes, it's a good predictor, but maybe it's completely unrelated to your causal relationships, you know? And with a descendant, it happens the same thing. So imagine that the person has a heart disease. This is a proxy for the fact that the person is obese, for example, and then you can have the same reasoning, right? So again, conditioning or observing the value of a descendant of a collider creates these associations between two variables that were originally independent. So those are very important triplets in the field. And it seems very basic, but gives you the intuition about what is represented in these graphs. And you see that this structure gives you something different from the first two. So it's even the opposite. So now X and Y are independent, but conditioning either on the collider Z or on the descendant of the collider W, you have the statistical association between X and Y. So if I have observed these two statements that X is dependent of Y and X is independent of Y, I can definitely say it's not happening what's there. I'm in these two cases. But if I observe that, I can eliminate the possibility of these two. So you see that's adding constraints. I'm not longer here working with two variables. I'm working with more variables. And more variables induce some constraints, which is related to probability, conditional independencies in the data, that allow us to create different graphs to explain these dependencies. Okay? And let's see some tool that's very important. Oh, yes, I want you to know that in these two cases, Z is a non-collider and Z there is a collider, right? So those top terms are important. But let's see a notion that's going to be important. So we have this notion of active or inactive triplets. So an inactive triplet is always relative to a set. It's going to have, so it's going to be inactive if the variable in the middle, which is the Z, the VM is the variable in the middle, right? So we have a triplet. Let's see some examples. I think it's easier. So the triplet has three variables, and the variable in the middle here has to be a non-collider, if that's the case, right? So if the variable in the middle is a non-collider, and it is in the set Z, so inactivity is always relative to a set. So if the variable here is in the set, then the triplet is inactive. Non-collider and the variables in the set is inactive. The other situation is that the variable in the middle is a collider, okay? But none, so the variable itself, the collider itself, and none of its descendants, it's in the set of variables that I'm talking about. It's the case exactly that we were talking before, right? So this set is going to be the set of conditioning, right? So we are conditioning on this variable. So if I condition on a non-collider, I make the triplet inactive. If I don't condition on the collider, the variable, the two variables here are already independent. So not independent, but the triplet here is going to be inactive, right? As long as I'm not conditioning on the variable, on the collider, on the descendants, this is already inactive. And with this, I can define the separation. So a path is just a path, is said to be disseparated or blocked by a set of variables Z, if and only if P contains an inactive, only one, you just need one, inactive triplet in it, right? So a set Z disseparates two sets. Now we are expanding this to a set, if and only if Z blocks every path between a node in X and a node in Y. So we will see examples. And we will denote with this notation here. And there is a G saying that this is in the graph. So it's a disseparation in the graph that says that X, the set of variables X and the set of variables Y are disseparated by Z. Let's see an example. So this is just one path and just one variable in the set X, one variable in the set Y. So X and Y. And I just need one triplet to be inactive to make this entire path inactive or blocked, and then make X and Y disseparated. So what happened if the conditioning, which the set C, is the empty set? Do I have an inactive triplet between this? So I have two triplets, right? X, B, and W, and B, W, and Y. If I have a non-collider, the triplet is only inactive if the variable is in the set. So the empty set tells me that B is not there and W is not there. And these two triplets are non-colliders. These two variables are non-colliders in these two triplets. So these two triplets are active. So the entire path is active, which means that X and Y, they are not disseparated. You can think about like flowing information. Maybe that helps to get intuition. Like if there is no collision, the information is passing through. So here I have information coming from X that's reaching Y because the path has no collision. If I condition on some variable, I create the collision. If I have a collider, I already have the collision. So since here the path is open because I'm not conditioning on any of these non-colliders, the information is passing freely. So in this case, the empty set doesn't separate X and Y. What about B? I'm conditioning on a non-collider. Is blocking or not the path? It's hard, I know. Everyone takes a long time to get intuition about the separation. But the idea is just look if it's a collider or non-collider. If it's a collider, it's already making the triplet inactive. If it's a non-collider, the triplet is active. And here I have two triplets that are active. So to make it inactive, I need to put on the set. So if I put B, I have one triplet inactive, and that's sufficient to block the entire path. The same with W. Is the second triplet, I just need one. So if I put the W there, I block the entire path. I can put both, it's just redundancy. Okay? Now let's see the second example. Now I have two triplets again, but I have a collider in both of them. So B is a collider in the triplet XBW, and W is a collider in the triplet BWY. And this path that has two triplets has two triplets that are already inactive because they are colliders without putting any variable in the set, right? So that's, if you see is empty, those two triplets are already inactive. But if I put B there, I'm going to make the triplet XBW active. So conditioning on a collider, I open the flow of information, as what happened with the obesity example, where once I know that the person is obese, I created this association between diet and exercise. So conditioning on the collider creates association. So here I created an association between X and W by conditioning on B. However, W is intact. I didn't observe yet, or in this case. So the second triplet is blocking this information. So if I just condition on B, I still have this separation. It's passing through the first triplet, but you block in the second. The same with W, right? Symmetric. What happened with both? Then it's passing through, right? So it's no longer separated. I have a third example that's a bit harder. I know that was hard enough. But it's just for you to have a notion that exists this type of structures. I have X and Y again. And what happened with the empty set? Now I have two paths between X and Y. And I need to block both because it's like information. The information wants to go from X to Y. And if the path is allowing me to pass through or creating associations, it's going to reach Y. So that is one path here that has B as a collider through this bidirected edge. And that is this other path that's just directed edge from X to Y. So if I condition on nothing, right, the empty set, what happened with the first path? Is blocked, right? That is a collider. But what happened with the second path? Is passing through, right? So X and Y are disconnected, it's not separated. So doesn't work for this separation. What about conditioning on B? Or like using B on the set C? What happened with the first path? As I said, conditioning on the collider creates an association. So once I condition on B, that is this path that has only one triplet, and it makes this active, so created association. It's done. I can even look at the second path, but doesn't matter. As long as I have one path connecting, is sufficient to create association. Let's look at, so B is not. Let's look at W. So W, okay, W is keeping, it's kind of hard, this one. Because let's look at the second path first, this directed path. If I condition on W, I'm blocking this triplet, the second triplet that has a non-collider. So the information from X doesn't reach Y through the second path. But W is a descendant of the collider in this path. So once you condition on W, you create an association between X and Y through this first path. So in this case, W also doesn't work, right? Because the first path is open. What happened with B and W? Again, we just need to check if that exists one path that's active. When I condition on B, I already opened the first path. I can stop already. It's not separated. So although this is represented as X without an edge between X and Y is always associated. This graph is representing a case where X and Y is never independent given any set. Okay. And yeah, so this is called inducing path in the theory, in the field, but basically you need to know that this separation not always is related to the known edge. Okay, the known edge doesn't mean no separation. All right, so this tool is extremely important. I'm going to finish just this part because once I have this separation on a graph, I have this implication. This is called global Markov property. Of course, it's an assumption, but once we create a Bayesian network, the goal is that every this separation on this graph is corresponding to an independence. This separation is corresponding to an independence in the distribution. If you have this, you have a Bayesian network. I think I have here the note. Yes. So if a Bayesian network, they are minimal independence maps. If for every independence, for every disseparation in the graph, this implies independence in the distribution, then it's a Bayesian network. So, and it is minimal because you can always create like a full graph, right? A fully connected graph. So there's no disseparation there. And then this is trivially satisfying the case that is implying a independence in the distribution. But we want that this is minimal in the sense that I cannot remove any edge without seizing this property. So it's a minimal independence map. So if you have an observational distribution, you can try to construct a Bayesian network that's satisfying this property. And if you follow the idea, which parent, so parents are these variables that are pointing to the variable, right? And from any Bayesian network, this factorization is holding. And it comes from the chain rule, because a distribution, a probability distribution can always factorize using the chain rule. Then you apply the condition dependencies to simplify each term. And then this always is going to end up with this factorization. And it's a little bit different from when you read Bayesian networks under the situation where you have no unobserved confounder. You see that there's a U variable there, but that is still this factorization of every variable VI given the parents, and the parents can be observed or no observed. Okay, and that you can easily prove this. And just an example. So if you get this this graph, again, there's no causal semantics here. I'm just putting edges everywhere. As long as through this separation, this property that every disseparation is connected to independence in the data, in the distribution, this is going to hold. So here I just put the chain rule for like these 5 variables. Then for every term, I look through, like I imply this separation in the graph, and I remove the variables. So for example, W and X, actually W is disseparated from here, W is separated from all these three variables given Z, because Z is a non-collider, so you have like this separation. And in the distribution, this is going to be corresponding to our independency. So you can, okay, my animation is just one by one. You can, for each of those properties in the model, you can simplify the terms. And you see here for the first that I can remove X, Y, and A because they are independent of W given Z, because this separation implies an independence in the distribution. You can simplify. And you can simplify, and then if you check this, you see that every variable is given the parent only, not the other variables. So Z given X and Y, you see, it's just given the parents. But if you change, I changed here. So you go back, you see that was different. So I changed the orientations, but this is not changing through this separation. You can check again. You have exactly the same set of conditional dependencies and independence, so you can apply the same reasoning, and then you get exactly on the same thing. And the point is here that I can change the causal semantics if you think that those are causal relationships, but the point that this is just an encoder of conditional dependencies, you cannot extrapolate these adds to be causal, right? The goal is just to codify the independencies and dependencies in the data. I will stop here so we can go to the break, to the coffee break. Maybe we can take questions just up to this point. Okay. Okay, I'm trying to move a little bit faster than before, but please interrupt me at any time that you are not understanding anything. Just put your hands up. So in the beginning, I tried to give you a very important vision of the field because of many people forgets about what actually causality is, what's the goal of causality when they are like publishing papers. So the fact that you use causal tools not necessarily mean that you are trying to reach this model of reality. So once you have this in mind, you will see that many of the directions of research in the field are a little, so it's hard to, if you don't have this vision, it's hard to put everything together. But once you understand this, you see that everything is connected. And there are many frameworks, for example, the potential outcome framework, UDEPRO framework, it seems like they are completely unrelated, but they are talking about the same thing, right? So it's just using different language. And here I'm going to try to ground a little bit more. What is this? So in the beginning, we in the first part of the lecture, we saw that we have this equivalence of modules in the sense that they are encoding the same set of dependencies and independence. This model, this class is called Markov equivalence class. So just to illustrate a little bit, like we have different models, right? And they are all inducing the same observational data. You could have like different models by changing the parameters and create exactly the same data. And that's an equivalence that makes us hard to infer causation. And if you have, this is just a summary, right? So if you have, for example, just that the X is dependent of Y, you would have like different ways of explaining the joint probability through the factorization that we discussed. In a sense that we could create different Bayesian networks to represent the same set of conditional dependencies. In this case, it's just one. And you would see that all these models are implying that X is dependent of Y, right? So this class of all these models, we could enumerate them, is called Markov equivalence class. So every model in this class implies the same set of conditional independencies through the separation, the two that we just saw. So that's kind of an illustration that correlation doesn't imply causation. So let's move a little bit, let's change a little bit the set of dependencies. So now suppose that I have everything dependent except that X is independent of Y given Z, right? We saw this already, and but if we try to explain this through different factorization, so we have like the chain rule and we apply this independence of X and Y given Z, we can create different Bayesian networks to represent. So I would just list here, but you see that in all of them, we are applying the fact that X and Y are independent given Z and simplifying the terms. And this creates different modules. So any two modules that are implying the same set of condition dependence, they are called Markov equivalent, creating this class of this class that's called Markov equivalence class. If if you have a measured or an observed confounding, you would also have different graphs explaining the same the same constraint, and this class is much bigger, right? So basically, you can, as long as you have Z here as a non-collider, you have the idea that X is independent of Y given Z. We just saw this through the separation, and this class is larger when you have unmeasured, unobserved confounders. But it's the same class, right? So under we call, when you have no unobserved confounders, we call this Markovian models, which is related to this assumption that we call causal sufficiency. But when we don't have, we should consider these possibilities of association through just unmeasured, unobserved confounders. However, you see that in all these modules, there is something that's invariant. The fact that Z is always a non-collider, right? It's never a non-collider. This is something that you can learn. It's a constraint. If you change now to the case where X is independent of Y, we now can list all the modules by applying the chain rule and then applying that X is independent of Y. And in all these modules, you see, again, an invariance that if you have, and you can even look here that if you have no bidirected edge, that's the only module that explains this independence. And but if you have an observed confounder, you have many more. However, in all of them, you have this fact that Z is a collider. So you can learn, even though you have only data, you don't know what is the causal structure. Maybe you have no identifiability in the causal structure. Maybe you don't have identifiability in the causal model, but you know you have invariances that are learnable from data. And this invariance is going to be important later for causal discovery. When you move to, so what is the difference between Bayesian networks and causal Bayesian networks? In the field, we have like a different term for causal diagrams. We can sometimes call this causal Bayesian networks or causal diagrams. They are all the same. But there is a difference that's fundamental here, that this graph is no longer just encoding conditional independencies. It has something more, which is representing causal and confounding relationships that are that are implied by the structural causal model. So you need this correspondency between what is a cause in the model to be now implied represented as an edge in the graph. Let's just define very quickly how it's very simple. It is intuitive. You probably got it already. But imagine that you have this structural causal model. And we have to, it's a procedure with just two conditions. So for variables that are in the set V, right? So we just look at the observed variables. We will have an edge that's pointing, that's going from Vi to Vj, if Vi is an argument of the function of Vj, right? This is something that we discussed already. So if this is the argument of the function of this variable, we have this edge here. And in the graph here in our example, we will see that B, for example, is a function of A and D, right? A is a function of just U variable, so you don't add any edge here because it's not in the set V. But B has A and D as causes, right? So arguments of the functions of B. So they are going to be pointing on the variable B. So you see that that's more than just condition independencies. It's like telling you exactly the order that's in the true causal model. This can be wrong, right? So it's an assumption. If you don't know the structural causal model, but you know the order of these variables, you can construct the causal diagram by hand. But here we are just seeing a correspondency, right? So if you had the structural causal model, you can easily construct the causal diagram. And so here we have A and D pointing to B, and C is a function of B. So you see this edge here pointing to B. That is another condition here to construct, which is related to these U variables. If all the U variables were observed, you would follow the same reasoning. So you would just point these variables as long as they are arguments of the functions, you put them pointing to the variable, like UA is pointing to A, UCD is in both here. So you point, UCD is an argument of both C and D, so it's pointing here and so on. However, this is too many, right? So there are so many unobserved variables that to simplify the representation, we just have this other condition here that only matters for this representation and for the inference later if this variable is causing two observed variables at the same time. So these variables that are just causing one variable, they are not problematic for inference later. So we are not going to look at them. But these variables that are pointing to two variables at the same time, they are very important. They are called confounders. And we are going to represent them as a bidirected edge. So we just do this with this that was shared, and all the others we will hide. Right? So when you look at this graph, you just need to think as this like a very simplified representation of this bigger module, right? So there are variables, latent variables causing A, C, D, and B, but the only representation here, what only matters are the directed edges, which are causal functions, and the bidirected edges, which are confounders, unobserved confounders. So if you have this graph, then you can this guarantees, like if you construct the causal diagram following this procedure, respecting every function in the structural causal model and confounder in the structural causal model, this graph, which is a cyclic directed mixed graph, a DMG, is going to represent all the entire collection of interventional probability distributions, not only the observational probability distribution as in a Bayesian network, but now we have this entire set of interventional distributions by changing who is the variable X here. And it's going to imply this factorization, which is almost similar as the factorization before, but with the fact that we are changing the variable X to a constant, the probability of X given the parents is 1, because I set the X variable to one value. So there's no probability of changing, it's always 1, the probability of X being as constant. Then you basically remove this factor from the factorization and everything else is the same. And it's hard to deal with this factorization, but that's the implied factorization from the model, okay? So that's called truncated factorization in the field. And we are going to now see one important task in causal inference, which is effect identification. And for the moment, we are going to assume that you have the causal diagram. Okay, you have knowledge to construct this causal diagram. I'm following here how the theory was developed over the years. So we started by assuming that you have this. So the causal pipeline, I would say the classical causal pipeline, has 3 important inputs. The first is a question. So you need to start with a question. So what's the probability of Y given to X? And you try to model the system by only using structural constraints, which is a causal diagram. So this has causal meaning. It's not a Bayesian network. If you have any method that learned a Bayesian network and you are getting this as being your causal Bayesian network, you are making a big jump by saying that one of the graphs in your equivalence class is the one that's implying the causal functions. So you have to be careful. Here is a causal Bayesian network. And so you start with this and the distribution over these variables that can be estimated from data, right? So we assume that we have the observational distribution in this pipeline. If you don't have, you just estimate from data. And those are now, we feed this input to an inference engine. This is now a very abstract engine, but we are going to see the pieces of it over this lecture. And one of the tasks that this engine can do is effect identification. What is effect identification? It's answering this query. If you are able to have an expression from this given your input, you have identifiability. So the solution can be yes, and yes means that you have an expression mapping. Mapping the distributions that you have available. So these are like the probabilities, the observational distribution. So this is just the conditional probability of y given x and z, probability of z. And this is just a function of these conditional probabilities. You don't need to think about this function right now. But the important part here is that you have a way by looking at this input to have an expression for something that has a do operator. So you haven't run, so this is not it's referring to a hypothetical intervention. I don't need to run an experiment to have the do. But if I have access only to observational data and then estimate the observational distribution, then these are like, this is the function to map to my interventional distribution. Got it? And I need this three input, right? So to have this. Once you have the distribution, like the probability distribution, you can have like expectation, you can do whatever you're used to do with a distribution, right? So if you want, for example, the expected value of y given to x, you can just derive this from the distribution. There is the part of effect estimation that I don't think I will be able to cover here, but basically you can get any estimator for your probability for your conditional probabilities and then plug in here, right? So there are some clever ways of estimating this right side of the equation here. So there are a lot of papers and works only related to the fact that you already know this equation. You already know what is in the right side of this, and you're just concerned about getting data and getting a good estimate for this. Just that, right? So for example, propensity score, causal matching, you have a lot of these techniques that are just concerned of getting data to estimate these probability distributions. But probability distributions you're used to do, right? So you can have any statistical method you can apply and get the estimations for this. But I would say the important part is to get this formula. And to get this formula, you need to formalize the constraints here in this causal diagram, okay? Yeah, once you have the estimation, just put a hat everywhere and that's done, right? So what is a causal effect? So a causal effect can be defined in many ways, but the idea behind it is just that it's a quantity derived from the probability, the interventional probability distribution that is going to tell you how much y changed due to an intervention. So the probability of y given to x is not the causal effect, but any quantity that you derive from it is going to be called causal effect. And in the field, you have different papers saying different definitions. So a very common definition of a causal effect is the average treatment effect, which is just this difference. So you assume that the variable x is discrete or could be binary, for example, and you want to know the difference between one level of the variable to another, and you define this the average treatment effect. If you have, but you know, this expectation can be derived from the probability distribution. So through like the usual formula for the expectation, and then you can basically use this definition. If the treatment variable is continuous, then you have a different way of defining the effect, right? So in this case here, we have the average treatment effect by being the partial derivatives of every variable y given every variable do x. And it's the same thing, right? It's just showing the rate of change of y, the rate of change of y with respect to this intervention. But you see that doesn't matter how is your definition. What matters is that you need the probability of y given to x to then apply these expectations or derivatives and so on. So I won't fix any definition for causal effect, because for me the goal is to estimate the probability of y given to x, right? So the classical causal effect identification, as I told you, has this pipeline, and I mean, there are many tools that allow you to derive this function. But the important part is, like, if you change the graph, so now it's a different graph, you have a different formula. So it's going to depend on the graph. And you have do calculus, you have graphical tools, you have many tools inside of the graphical framework of causality that allows you to just derive this equation here on the right side of the equation, this mapping the right side of the equation. But there is an algorithm that I think is very important for you to know. That's the ID algorithm. That's in this paper by Jin Tian and Yuda Pro in 2002, that given a causal diagram, you can, it's a sound and complete algorithm, right? So given the causal diagram and the observational distribution, if the effect is identifiable, because there is an if here, but if it is, the algorithm is going to return that expression for you. I won't have time here to explain the algorithm, not even the do calculus, but I would try to, at least one of the graphical tools, I'm going to try to give you details about it. But that's the classical view of effect identification. You have a causal diagram and your goal, and a research question, right? A query. And if you have enough information on this graph here that allows you to identify the effect, the algorithm is going to give you. Note here that there is a big assumption that you have the causal diagram. You have knowledge, structural knowledge available to construct it. So what is the effect identification problem? You don't need to read this. This is just I'll give you the intuition behind it. But the idea is that, as I told you, you have the true model. This true model not necessarily is known. But if you have the causal diagram corresponding to it, plus the observational distribution induced from it, of course, there are other models that imply the same causal diagram and the same observational distribution, right? So we saw it. The goal of effect identifiability is that doesn't matter what is the causal model. You are going to just look at those. And if you have an expression that fits perfectly, like it doesn't matter what's the model here, if for any graph and any observational distribution, you have only one expression, then you have a way to know what's the distribution implied by the true model, because it's the same for all of them, right? Because it's just one. Doesn't matter what's the model behind it. If you have this, it's only one distribution for all of them, you have identifiability, and then we estimate this. So if you have like if you prefer like a picture, you have, for example, all the models that are inducing just the observational distribution. We are describing here in yellow. Also, you have different models that are implying or inducing the same causal diagram. In the intersection are all of them that imply at the same time the same observational distribution and the same causal diagram. If for all of them, you have the same probability of y given to x, then your effect is identifiable. right? Your probability of y given to x is identifiable. But if for at least one in this entire class, if you have at least one that the effect is identifiable through a different mapping, or it's not identifiable, then you cannot tell which is your expression, because you cannot rule out the possibility of that one is being your own your true causal model. So you will have like a negative result. In the field, we have partial identification. This is going to be a topic that I will give a few references in the end, where people, even in the scenario where you have a negative answer, you try to get bounds of the effect. But that's kind of the goal of the task. Like if you have a way to ignore what's the true causal model, but you have like equivalence in this in the graph and in the probability distribution, and you have also for all of them all the same expression, then you have identifiability for the probability of y given to x. Is this clear? Okay. So a very simple criterion that's very basic, but it's very well known, is this adjustment over parents. And the idea is that if you have all the parents of a variable x observed, then the effect of x on y is identifiable. It's very simple, but of course it's strong. You need all the parents. Why is this? Because if you have all the parents, then you have no u variables here, and then you have this adjustment. You see later how you derive this. But basically, it follows from the truncated factorization that I showed to you. You can always get this. So as long as you have the parents of x, you can just write this summation. So it's just the sum of the probability of y given x and the parents, and you also multiply by the probability of parents. So there is this adjustment over the parents, because this sum here is just averaging for every possible value of the parents, the probability of y given x and the parents. And the proof follows directly from there, and you can see here an example where this could happen. Like you have x and y, and you have many variables affecting x and y in this explained through this causal diagram, okay? And you see that the parents of x are all observed. You have no bidirected edge between z1 and x and z2 and x, which means that you have no variable, no argument of the function of x that's not observed. You have the u's that are not causing x and z2 at the same time, and x and z1 at the same time, right? So those are the confounders. You can have other causes as long as they are independent of your other parents, but you don't have any bidirected edge between z1 and x and z2 and x. Those are all the parents that you have, and they are all observed. If you are under this scenario, you just do this summation, and that's done. It's pretty simple, but many people are kind of using the argument that if you observe and observe it even more variables, you reach you satisfy the criterion that you observed all the possible parents, and then you'll be under the scenario. This is just a simplification of, I would say, a more general approach, which is called backdoor criterion, that you don't require this. You still need the graph, right? So let's assume that this is your graph here. And let's say that x is your set of treatment variables, y is your set of outcome variables. And if that exists a set z such that now we are going to use this separation in the graph where we have this notation here. This is just the graph that we have after cutting the edge out of x. Let's see if I have here. Yes, we have here. So we remove every edge that's out of x. And we keep only those variables, those paths that are creating confounding. Those paths are called confounding paths or backdoor paths. And you see that by blocking these confounding paths, we are removing the influence of, or removing the parts that are creating association between X and Y that's not due to causal effects. If you block everything that's confounding through a set of variables Z, right? So Z separates X and Y in that graph here. And the set Z has no descendant of the variable X, then you are in a very special scenario where the set of variables is called being admissible for backdoor adjustment, and we'll have a very similar formula as the one for the parents. Here, it's a case where Z is also a parent of X, so it's a very simple scenario, but we'll see in the next slide that not necessarily can be the case, right? And it's exactly the same formula. It's just changing who is this set Z. If you have all the parents observed, then you put Z as being all your parents. If you don't have your sets, all your parents observed, you need to check if that exists a set Z, such that after conditioning on the set, you block all these confounding paths. And you see that this is a simple case, just for illustration here, that there are two paths that are confounding X and Y. And through this separation, this is non-collider in both paths. So after conditioning on Z, I block the two paths. So I'm blocking all the confounding paths. And the adjustment is going to mimic the fact that I'm removing the influence of this confounding, and then I'm going to just leave the causal paths open. So this is going to be your causal path, your causal effect. That's the idea. Let's see a more complicated graph. So as I said, X and Y don't need to be just one variable, can be a set. So here I want to have the set X being X1 and X2 together, and the Y is just the variable Y. First, I want to check if there exists a set that's composed only of non-descendants of X, and X is X1 and X2, so cannot be descendant of both, and that at the same time blocks all these confounding paths. Okay, that's the graph after removing the directed edge out of X. So you see that I removed this edge and that edge and also that edge here. So I'm left only with this confounding path, which is creating an association between X2 and Y. And as long as I have like two variables, I have a set of variables that's going to block this path, and this variable cannot be a descendant of the X, then I'm fine. Maybe it's a hard question, but can any of you here can see which set can block? I cannot have a descendant, so that's, I think, is the first criterion we have to check. So which variables are descendants of X2 or X1? Z1 is descendant of X1. Is that all? Yeah. So I cannot use Z1. Now, Z2, can I just use Z2 to block this only path that I have here? Yes. So Z2 is admissible for backdoor adjustment. So if Z here is equal to Z2, then you can just replace Z with Z2, and I will have my adjustment formula for the effect of X on Y. But if I use Z1, I get the wrong answer. I cannot. So that's why you need the graph to know which variables allow you to have the causal effect. You cannot blindly get any variable and assume that this is the true covariate set. I have more examples here, but I think I'm over time, so I'm going to skip a little bit this part, but you can check later. So basically, you just need to check what are the confounding paths and see if you can block. And I want just to stress here that our case where there's no set that allows you to do backdoor adjustment, which is the last one. So the last one here, I have X and Y. I want the effect of X and Y. And I have two confounding paths, one through Z1 and one through Z1 and Z2. And once I condition, so this path is blocked, right? Is a collider. But the other path is not. So I need to condition on some variable to block one of the conditioning on the confounding path. But Z1 is a collider. So if I condition on Z1, I'm going to open this first confounding path. And if I condition on Z2, I'm going to also open the same path because it's the descendant of this collider. So the lesson here is that not always we can get the set of variables we have available. So suppose we have X, Y, Z1, and Z2 as your data set and say, okay, my set of covariates are going to block my confounding paths, and then I'm going to apply this formula and get the causal effect. That's wrong. And for those scenarios, you need more sophisticated tools. We have the idea of minimal backdoor adjustment sets. Those are important to know because also if you condition on many variables, you also reduce, you have numerical instability, right? So you don't want a large variance of your estimator. So you always have to look at the minimal backdoor adjustment sets. But that's something that you only look after you have a conditioning, a set of that's admissible for adjustment. So that's a very important tool, although it's very simple. There is this website that I would recommend you to sign up. It's like causalfusion.net, where it's also developed by Adia's Barenboim group. Basically, you can draw your causal diagram there and ask many questions related to causal inference. So that's one example where you draw your graph and you can ask you what's the effect of X on Y, and it's going to give you the adjustment formula that I just told you. It's internally, it's running the ID algorithm, right? If you have like a different graph or a different graph, you see here, this is a case where you have a confounding with X, but still Z is a case where Z blocks the confounding path, so it's still the same formula. And if you have a case where there's no way to identify the effect, it's going to tell you as well. And it's not only for backdoor adjustment, it's running the ID algorithm, so it's always complete in the sense that if you have no identifiability, it's because your graph is encoding, there's no knowledge enough there in your graph so that we can identify the effect. If you also, if you are from economics, especially like where you worked already with the potential outcome framework, you may have heard about the conditional ignorability assumption. So this is something that people call it like usual assumption for causality. Who have heard about this? Conditional ignorability or conditional exchangeability? You. Yeah, so this scenario, so I would say that's a lot of people are under the potential outcome scenario, and they don't realize that you are under a very specific assumption when you are assuming this. When you're assuming conditional ignorability, there is the theorem by Pearl that explains exactly what is this assumption. If there is a set Z that satisfies the backdoor criterion, as we saw it, so we just saw some examples where there is no even a possibility to find this set. But this independence, I won't go into detail here, but that's the potential response of Y after an intervention of X being independent of the treatment variable given a set of covariates. You may be very scared about this notation because it is scary. So I would say that no one understands what this means. And that was the reason behind Pearl when he developed the graphical models. Is like, you ask someone to say, if that's true, you follow my theory. It's the potential outcome framework. Basically, many of the methods, they are under this assumption. And the assumption is requiring you to check if this potential response is independent of the treatment variable given the covariate set. When they say this, there is an equivalence that says this is only true if the set Z satisfies the backdoor criterion. But this is not an assumption. You don't need to use this as an assumption. You can have, of course, you are transferring the requirement to have a causal diagram. But if you are transparent in the sense that you draw your causal diagram explaining the knowledge that you have, then you would see that this assumption is requiring that the set of variables that you have in hand is blocking these confounding paths and leaving you just with the causal paths open. So this is usually framed as an assumption. And there is a way to prove this. So we have this idea of counterfactual graph, because this variable, this potential response, is a counterfactual variable. And then we put together two worlds. So this is the observational world together with the hypothetical counterfactual world. And then if you have the independency through this separation of that variable, that's the response variable, and the treatment variable x, then you apply the separation here and see that you have indeed the separation of that variable and x given z. And see here that's all colliders. So you construct the counterfactual graph given the causal diagram. So even though you say, I'm not assuming a causal diagram in the potential response, in the potential outcome framework, you are assuming that you have a graph such that when you put together with the counterfactual world, you have the independence there. So it's not, I mean, you are under very specific scenarios. So you have to be careful when you use these tools to see if actually these assumptions are holding. So that's only a very important note, because many people are just blindly using this assumption and believing that in the end you have the causal effect, and you have, but as long as your set of variables is blocking the backdoor paths. Okay. When you put this knowledge into in a form of a causal diagram, you have, I would say, you open many doors, because now you can see different ways of obtaining the causal effects of interest. So if your graph, for example, the front door graph, if you try to apply backdoor criterion here, you see that between x and y, there's no even a way to block this confounding path. It's a bidirected edge. There's no way. However, there is a way, a different way, which is the front door criterion, that I won't go into detail here, but you have a different formula. So that is a way to identify the effect of x and y, even though you haven't observed all the confounder variables. You just need to apply this calculus, the do calculus, or the ID algorithm, or this criteria. And by changing the graph, you change the formula. So this is the conditional front door, that's the napkin, and see the formulas are all different. So you can put your name here in this graph. There's no name, but you have different formula. And it's impossible to deal with case by case. But you know, of course, if you want to assume that you are in a specific scenario in work on only the estimation of these components here, you'll be fine. But you need to be aware about what are the assumptions behind it. And the ID algorithm, it's going to deal with any graph, right? So it's complete. Any graph that you have as input, you put there and you have a formula for it. This is implemented in many packages, Python packages, R packages, I would say we have here in the next slide, we have tools for it. And I also want to stress that if you are under the scenario where you assume that you have no unobserved confounder, it's very strong, right? And we call it these Markovian models. Basically, every effect is identifiable. You don't need causality anymore. It's simple, right? It's so strong that if you say, I have all my variables that are creating confound observed, I don't need these tools anymore because everything is identifiable through the truncated factorization. Just need to estimate every component of the truncated factorization. Sometimes it's called G computation or G formula, and it's always identifiable. The interesting part starts when you don't have all variables observed. So you start having like all these tools. You have like adjustments of your parents, as I told you, where you have no unobserved parents. But you can go further and relax into the case where you don't know if you have observed parents or not. So you are under like this general idea of you have no unobserved, you could have unobserved confounders. So you can have the backdoor adjustment, the generalized adjustment, front door adjustment, do calculus, the identify or ID algorithm, and so on. So everything that I'm talking here is in Pearl's book. So this is very classical. And it's from 2000, right? So more than 20 years ago. Of course, and a lot of the idea algorithm came from the Jintian's thesis, is amazing thesis. I would say it's I would recommend everyone to read his thesis. It's really nice. But there now 20 years after that, and what we have is like now we have ways of identifying the effect by combining observational and experimental data. So for example, that is this paper by Lee and others that has general identifiability by any set. So it doesn't matter if you have experimental data over different variables and observational data also for like others, a different set of variables. So you can put everything together and then identify the effect given a causal diagram, right? So here is just giving a causal diagram. In 2021, we have this paper for also general counterfactual identification, also combining experimental data and observational data. Sometimes we don't want to deal with just this hard intervention. So when I told you that when you change the variable x to a constant, we are doing something that we call hard intervention. Sometimes in your applications, intervention is just changing the probability of occurring some event. And this is what we call soft or stochastic intervention. And we also have papers for calculus under these different types of interventions. There is also connection with deep neural networks, which it's in this paper by Xia and others, and also counterfactual estimation using neural networks. The idea is pretty simple. It's just basically, since you have the causal diagram, and this is very important, you're not learning, you're inducting, you basically fit a model where it's following a causal structure through inductive bias, and then you just check if your expression for the causal effect is the same by optimizing and minimizing the causal effect. So you're just getting the entire range of possible expressions for your causal effect, and if they all match, you have identifiability. So it's not magic, right? So we here are we are incorporating knowledge. I'm not against the Pearl's causal hierarchy here. There's the causal diagram there that kind of tell what is the assumptions or the constraints that you want to respect in this optimization problem. Okay, before moving, some questions before regarding identification, giving a causal diagram. Okay, so let me move. I would say that this is more a machine learning question, right? So what if domain knowledge doesn't allow you to construct a causal diagram? What should I do, right? So we could be very naive and say, let's try to enumerate all these possibilities and fit all of them. However, that is a super exponential growth in the space of, let's start with DEX. Let's not even consider the unobserved variables. So the space of DEX can be explained by this recurrency relation. And basically, I can give you a table here. So look, like if you have just 3 variables, okay, I can draw 3. I have like for 2 variables, I have 3 DEGs. For 3 variables, I have 27. So it's feasible for 729. But then with 8 variables, it's already 10 to the power of 13. I cannot do this, right? So enumeration is not a good idea. And this is not even considering unobserved variables. If you have now the space of ADMGs, which is considering the unobserved variables, that's the recurrence. That's actually the formula, and it's proportional to the number of DAGs. And here's just a comparison. So with 3 variables instead of 27, I already have 216. And with 8 variables is to the power of 21. So you see that the problem is NP hard, right? So it's impossible to solve, especially through enumeration. And so there are many algorithms that are trying then to understand given some constraints. So here it's without constraints. But one of the constraints that we just saw, are the conditional dependencies and dependencies in your data set. So one idea that people have is like, why not try to learn Bayesian networks? Now it's Bayesian networks that's just encoding conditional dependencies and dependencies in your data, and see there what are the invariances. Because it doesn't matter what's your causal Bayesian what's your causal Bayesian network. If you have an invariance, you have this invariance in all Bayesian networks, especially in your causal Bayesian networks. So that's the goal. So learning the Markov equivalence class, that is this idea, right? So many models, they are statistically indistinguishable without adding other assumptions, just looking at the conditional dependencies and independencies. And this class is called Markov equivalence class. These causal discovery algorithms, they can only learn up to the Markov equivalence class. It's an impossibility result. You cannot learn more than this class, right? I cannot have a more refined representation of your model without assuming something else. So here we are under this assumption that we are going to only use dependencies and independencies that are observed in your data set. So one of the algorithms that I would like to talk here is the fast causal inference algorithm. We have many algorithms in the field, and they are divided basically by this idea of if I have causal sufficiency or not. So this algorithm is not assuming causal sufficiency. If you are under the assumption of causal sufficiency, you can do a lot of stuff. You can scale much more, but then it's unrealistic in the sense that you have to assume that you have all the confounding variables. Here, this algorithm, I would say, is very powerful because if you deal with an observed confounding, you can have any set of variables you have. You can select any subset of variables, and the other variables are being considered now and observed, and you still have valid results. So if you have 5 variables or 1 billion of variables, if you have the result in 5 variables, this result is true with 1 billion as well. You have this marginal consistency. So you can start very small and see if you have the result there. If you don't have, then you start growing it. It should have like marginal consistency. And so you see that this algorithm is under this scale that we saw. It can learn reliably up to 10, 20 variables. But you cannot see this as a big limitation. Of course, we would like to expand this to like 100 variables. But if you have a result there, you can create adaptive algorithms. This is one of the research directions that we have today. So I would say that this algorithm, which was developed in 2008, it is still very important in the field. There are many variations of these algorithms by using this as the base, right? So I would say it's the most important algorithm so far. So how it works? So again, our illustration, we have different models that could explain the data, but from the data, we can extract the dependencies and independencies there. You can have a condition independence test, and you can estimate if the variables are correlated given some other variables or not. And then you can, you can construct this class by hand. I don't want this. But the algorithm is going to detect all the invariances. So the FCI algorithm is going to detect this through a set of rules, and is going to give you as an outcome this graph that's called partial ancestral graph. It is a representation of your entire Markov equivalence class by basically giving you these circles here. They allow you the construction of models that has the tail or the arrowhead there. You can basically, it's not that simple, but that's the main idea. But as long as you respect there's now something called M separation, which the extension of this separation for this object. But this object is encoding all conditional dependencies and independencies of your data. So it's a class of Bayesian networks, and everything that's not a circle is an invariance in this class. So the fact that I have an arrowhead on Z here means that all the models that fit to my data has Z as a non-ancestor of the other variables. And I'm calling here ancestral graphs because the edges, they represent ancestor relationships. It's no longer direct causes, is ancestor, although it still preserves the idea that if you intervene on this variable, there is a causal path that's going to affect the outcome variable. So you can learn something through this algorithm. So basically, arrowheads means non-ancestrality. So in this example, Z is a non-ancestor of X and Y. And that's the pipeline. You will start, so that's the unknown reality. Obviously, you won't know this, right? You don't know this. So you start with a complete graph. You have access to a conditional independence test that's going to tell you what are these dependencies and independencies in the data. And here there is a strong assumption that many people are working. I'm very active in this area by relaxing or at least not relaxing, but making the algorithm more robust under violations of the assumption that all these dependencies and independencies are correctly detected. Here, the original algorithm, you always assume that what we observe through these tests are correct. Modeling uncertainty and adding robustness to algorithms is a very active research area right now. But under this assumption in the original algorithm, you can basically remove every edge that's corresponding to a independence. So the fact that X and W can be are independent given some set, in this case it's just the empty set, makes you to remove the edge between X and W. The same for X and Y. It doesn't matter what is the conditioning set here, is by the fact that you found an independence makes you to remove the edge between X and Y. And then there are a set of rules. There's the rule 0 as well. So it's more like 11 rules, but in total, after applying these rules sequentially until you don't have a way to apply anymore, you have a graph like this. In this case, you can learn, for example, that W is an ancestor of Y and Z is an unconfounded ancestor of Y. So there is this green arrow here. There is a concept that's called visibility. It is in Gigi Zhang 2008 paper. No, it's in another paper by him, but it's the causal inference through partial ancestor graphs. That is the definition of visibility, and basically tells you not only that there is a directed path, which means that makes Z ancestor of Y, but also gives you the certainty that there's no confounding, an observed confounding in this edge, which will be then a necessity for identifiability of this effect of the Z on Y. You don't have this for W in this example. You know that there is a directed path from W to Y. So if you intervene on W, you have a difference in Y, but you cannot compute the effect size, right? So you have here, so causal discovery allows you to recover the directionality of the mechanisms, and effect identification allows you to identify or to quantify the effect size. In this example, you would be able to do for Z, the effect from Z to Y. And so we have all these relationships here. You see that arrowheads, they mean no ancestrality. So B is a no ancestor of A. In this example, we see that Z is a no ancestor of X and W. Y is a no ancestor of everything else, and so on. And the tail means that you have an ancestral relationship. So Z and W are ancestors of Y. Yeah, that's the conclusion here. So I told you that one of the tools for extracting these relationships is a condition dependence test. You have many in the field, and they depend on the type of variables that you have available. So if, for example, you have only Gaussian variables, you have like this very old test by Fisher, 1921. It's basically partial correlation tests. Like if you have a Gaussian joint distribution, then you can apply this partial correlation test and identify independency between the variables. Maybe you are not in this scenario, so you want something non-parametric. So we have, for example, this kernel basic non-parametric test is where you don't assume linearity or Gaussianity, so you can have, like, of course, when you relax these assumptions, you need more data to identify these dependencies and independencies, but you also have a way to do it. There are some others that use linearity. So if you believe that your data is following linear functions, you can apply like this other method. Sometimes when you have small data sets, assuming linearity gives you more power to identify this dependencies and independencies. If you have, for example, data that are correlated, so all these other methods, they assume that you have independent data, but sometimes you have like family data or you have like clustered data, and you want to deal with this. There are like basically ways to model the correlation among the observations and so on. So just to give you more examples about what a partial ancestral graph is let me just let's get our example. So we got this as the outcome, right? So this is the output of the algorithm, and I told you that this represents the Markov equivalence class. So if you try to enumerate the modules inside of the class, you would start by following the possibilities that the circle can be anything, can be tail or arrowhead. And this is just an ancestral relationship. So I want to just I want you to pay attention on this model here, where you see that W and Y, there's no edge, right, between them. However, there is a causal path that goes from W to Y. And that's what's represented in these graphs. You have ancestral relationships. That's why it's called partial ancestral graph. And this is sufficient for, like, if you want to intervene on W, you will see a difference, like a change in the variable Y. But this doesn't mean that the W and Y are unconfounded. And this is exactly one example where you could have a bidirected edge here. And this effect here it could be confounded. Let's see if I have another example that's interesting here. Oh, and you see that in every graph, you have this green edge. The green edge means that not only Z is directly connected to Y, but there is no bidirected here. It's impossible. I cannot add a bidirected edge between Z and Y. And it's really simple to see, because if you have a bidirected here, then you have a collider. At the same time, you have a directed path, and then X and Y wouldn't be separable. So you wouldn't have the separation between X and Y. So basically, these reasonings are part of the proofs of all these rules in causal discovery. Like you try to create a contradiction by seeing what would happen if you have an edge here or a different direction, and basically the data doesn't allow you to have. So that's why you have these invariances. Questions about this? Yeah.
The logic behind the green arrow. I know that you just said it, but it's not entirely. Okay. Could you maybe explain again the logic behind the green arrow? Because I know you just explained it, but it's not 100% clear to me yet. Why?
So you have, as one of the dependencies and independencies in your data, you have that X is independent of Y given Z and W. Okay. And yeah, so I will need to use both here. I will give you exactly how this is constructed. So X and W, they are independent marginally, right? So this tells me that automatically that there is a collider here, because it's that special case where you have independence, you have a path, and since you have marginal independence, you need a collider. So you learn these colliders. So for sure, you have this arrowhead here. And now I need the independence of X and Y given Z and W. I found this, so I'm trusting that this is correct, okay? Imagine that you have a confounding path going from Z to Y. So this would be a path that has an arrowhead into Z and also into Y, right? When I condition on Z, for sure, I open this collider. And the fact that I don't need any other variable to block this supposed confounding path that I told you, it means that this doesn't exist. You see, it's like I'm conditioning on this, so I make sure when I condition on a collider, since I have this arrowhead, I know that any collider that can form here is going to be open. So any open path would be a confounding path, and the fact that I'm not blocking it is because it doesn't exist, or it exists but it's not open. Could be like already with a collider here. So this is the test, actually. Visibility you can test by having a variable that's not connected to Y in the graph and has an arrowhead pointing to this first variable. That's one of the conditions for visibility. Is this clear? Okay, great. More questions?
Hi, sorry. It's not clear to me, why is it still possible to have the second model? Why can I still have a double arrow between W and Y? Because from what I understood, and I might have missed some parts, the model we have on the left is what we see in data. So everything that you have in red and the green arrow is modeled from our data. We've seen that, right? We've concluded that. Then I also think that the arrow from W to Y, so it's only one directional in what we've seen in data before. So why are we still considering the double arrow between W and Y?
So that's the true graph. And you are asking why there is something. Yeah. So this graph implies this set of independencies. Okay. So that's all I have. I don't have access to this graph. I have all this. When I learn this representation. This is a class that includes this module, but includes many other graphs. And when I listed there, so that's when I listed here, this is the class. That's all modules that are part of this class here. So this is representing a class. The true module, I think, is the first, if I'm not wrong. I think that's the true module. It's one of the class. I don't know. I just have this as the output. I will never have access to the true graph. But the second graph implies exactly the same set of independencies that I have here. Like X is independent of Y given Z. So here Z opens this collider, and then I condition again on W, so it blocks. And also X and W are independent marginally, right? So they are separated, so it implies the same. So this is satisfied by this graph. So that's why it's part. So I don't know if this answers your question. There is a gap here that I didn't explain. So from this model, you have a representation that's called maximal ancestral graph, where basically you just see what is ancestor. So for example, W is ancestor of Y, because ancestrality is just a directed causal path, right? It's a path that's directed. And this is a partial ancestral graph. So every time that I say that there is this edge here, doesn't mean that there is an edge in the causal diagram. It means that there is a directed path.
So could be an open, like you have the little circle. It could be an open circle there or not. Like in the, in
this
that model.
circle here could be.
Could we not have the same circle on going from W to Y?
So the circle is uncertainty. It would allow you to have also W not ancestor of Y.
Okay, now I see.
You understand?
It's
And
just
this is
a
not
nomenclature
possible.
problem. I wasn't totally sure. Thank you.
Okay. Oh, there's another question.
Is there a way to combine this method with maybe some partial domain knowledge?
Yes, yes, sure. I'm not in the end of the lecture.
Okay.
I will exactly tell you what are the advancements in the field, and definitely that's one of the most important direction. Yes. So this is just an example of several underlying causal diagrams. What would be the partial ancestor graph, just for you to see that that's the example we just saw. But there are examples where you learn a bidirected edge, which means that we know for sure that there's no causal relationship between them. The green arrows are like all these visible edges where this is just a necessary condition for effect identifiability. We will see later. But you see that we can learn. It's not always the case that you learn everything, but you learn sometimes enough for example, if you are interested in the effect of X on Y, and this is your case, you would have your answer truly through data, observational data. That's again a case where X and Y are identifiable only through observational data. Going beyond the Markov equivalence class, that's exactly the question that we had. And there are many exciting works. Some of you may say, oh, it's going back towards assuming strong assumptions, but how can you go beyond? Is exactly adding more constraints. There is no magic, right? The first one is like combine interventional data. I would say that's very, this is a very inspiring idea because you combine both, right? You start with observational data. So in large language models where we are right now, we have already knowledge that's, I would believe, that's sufficient to learn the equivalence, the Markov equivalence class that represents our language model. That's a very important question that we have to ask ourselves. Are we reaching identifiability through data only? Of course not. It's an impossibility here. We are always under this class. How can we go beyond the class? We have to add intervention. One possibility is like add interventional data, like you performing experiments. So you use this experiment, could be combining with reinforcement learning, could be like with A/B tests. You have other ways of getting interventional data, and but of course you can improve your model by doing it, but it would be interesting to understand how this is reducing your equivalence class. You don't stop by, okay, I have a model, because reaching identifiability of the causal model is not even the class it's not even the causal diagram. We are here trying to find the structural causal model. It's like the functional model. So refining this class in the sense that we are going to reach identifiability is really hard. So I would say interventional data is one of the most important steps that we should follow. And there works here, for example, that is this one, that if you have interventions, data from soft interventions, this is just a more general way of thinking about interventions. You can identify a class. It's a different class. It's called psi PEG instead of just PEG. You have like to define what is this new equivalence class. But this is one case. Another one that's really recent is just combining data from multiple environments, and you have to encode in the learning process what exactly are the differences between these environments, because although you have different data sets, they may come from different populations. So they have, like, for example, distributional differences that you can learn, and this is now part of the structural model. And this algorithm here allows you to learn where the interventions were performed and what are the variables that could explain the differences between the environments. So this is a very nice picture from this last paper here, that imagine that you have this, forget about this square, I'm going to explain, but suppose that this is your causal diagram. And you have data coming from two different populations. And this edge, it's just representing the fact that the data coming from one environment is different in the distribution of Z than in the other data set. And so you need some other variable that explains these differences between these data sets. Right, so it can be just a hidden variable, but it's affecting how Z is constructed. When you put together these two data sets, you need to explain the differences between these two data sets. And you can construct the Markov equivalence class by now seeing this this node. This is called the S node in the field. When you study transportability of causal effects, it's there. But you see that this is inducing some other associations. This is even an inducing path that we saw in the beginning that basically creates the association between this S node and Y. You could also have, this was an example from the paper, where here we had interventions on the variable X. So the interventional data was randomizing the variable X, and there are two data sets where they were in randomizing the X. So you need to also, so the algorithm, you'll be able, so this is, everything is learnable. So by just giving the data sets to the algorithm, it's going to detect where that is a distributional difference. So it's going to learn where are the S nodes, and it's also going to learn, because even if you don't know which variable was randomized in the experiment, you can run this algorithm and it's going to detect which variable was the target of the interventional data. So it is really powerful, and you can have many times, so in the end you have this S PEG. It's extension of the PEG, so it's no longer a Markov equivalence class, right? Because we are incorporating interventional data, and not only from one environment, but from multiple environments. So we will have like this augmented PEG that's called S PEG. And the class is usually smaller than the Markov equivalence class. You're going beyond the Markov equivalence class. That is another idea that's just incorporating prior knowledge. So there was a recent paper in the RIPS 2022 where it requires local background knowledge. Basically, you need to know for every variable if this variable is either a cause of your neighbors or caused by your neighbors. Sometimes this knowledge exists. I would say, for example, interventions gives you this knowledge, because once you intervene on a variable, you will see the implication on the neighbors. So everything that changed after an intervention is a descendant. Everything that not changed is no descendants. So they argue in this paper that's a not strong assumption to have. but you could incorporate, and it's a complete algorithm. It's sound and complete, including background knowledge of this type. So this is a recent paper that is still in archive, but it's going in this direction of solving two important issues in the field. The first one is modeling uncertainty. So here we have a probabilistic causal discovery algorithm that's, instead of just learning one peg, we are enumerating basically all the ancestral graphs that are feeding to the data. You need a score here, but you need a distribution of all these ancestral graphs. So of course, if you had no background knowledge, this would, like the mode of the distribution would give you exactly the graphs inside of the Markov equivalence class. But here we created this human in the loop approach where we ask the user what's the optimal association that you could give me to optimize the distribution. So here we are minimizing the cross entropy of the distribution, but basically I could interact with the human and ask, what do you believe is this, or so we have this picture here. We could ask, this is just the distribution that came from the observational data, and then we ask, what would be the edge between 2 and what do you believe it's the correct orientation between 2 and 1? And it can be noise. The human can say, I have just 30% certainty that this is in this direction, could be also in the other direction. But we use this to update our distribution of graphs. So basically, we are at the same time modeling uncertainty and allowing to incorporate background knowledge. So we don't longer here use the Markov equivalence class notion. We use the distribution that's updated after incorporating prior knowledge. So it's going in this direction that you asked. The other ideas that people are using is like, let's maybe add linear models. So linear models are coming back they're very strong also in the field, because when you assume some constraints in the distribution or in the functions, you can detect some asymmetries. So a very famous method in the causal sufficiency, which is called Lingan, was developed in 2006. And in this paper in 2014, they discovered, they proposed this causal ordering method that's called parse Lingan, where you can have an observed confounding. And even in this scenario, you can learn all the causal orders in your data. And you have identifiability if your error terms are non-Gaussian. It's kind of too much, maybe, like I need linear functions and non-Gaussian errors, but they relaxed the fact that you need causal sufficiency. Here in this paper, Shimizu asked also causal sufficiency. In 2014, they relaxed. They say that you don't need this anymore. And recently, Wang and Durton, they proved that the algorithm here from parse Lingan is actually sound and complete. So actually learns all the causal orders. And the causal order is what gives you the ancestral graph. So it gives you only identifiability of the ancestral graph. And they also propose like an extension for, we call it both free graphs, which is a little bit more, so ancestral graph is a class of ADMGs. When you say that's a both-free graph, it's just one type of ADMGs. So it learns a little bit more than the ancestral graph, but you need to require that this is a both-free graph. But you see that people are moving a little bit towards going to refine the class, but sometimes you need to be careful. You need to know if these assumptions that they are doing are actually fitting your application. Another one is additive noise models. So also very recently, they tried to I don't know if I have here. Yeah, like there was a paper that's the A&M additive noise models that under causal sufficiency, they proved that under nonlinear functions plus Gaussian noise and causal sufficiency, you have identifiability of the causal structure. But recently they relaxed a little bit this idea of requiring the causal sufficiency by requiring something that's closer to the independent causal mechanisms. It's still asking something very related to causal sufficiency, but it's relaxing a little bit more. It's more about modularity. And they go beyond. They proved that they showed some examples where you can learn more. They actually proposed this causal direction criterion that you can orient a pair. So you have just two variables, and because of these assumptions, these constraints in the distribution, they sometimes can learn if it's one direction or the other, but you need these assumptions to be true. Dynamic systems. So a very important paper extended the field to allow cycles. So I told you in the very beginning that we assume acyclicity. However, we have now some works saying that, so they extended now, for example, for partial ancestral graphs, you have the extension of this separation to M separation. This is assuming cyclicity, but now they have something that's called sigma separation. And they proved that the FCI, the algorithm that I just showed you, if you use sigma separations on top of this peg, you can recover a class that includes cyclic modules. So we are already learning cycles, but you just need to understand how to characterize these modules. So there's this paper, there's many other papers that are establishing what is actually a Markov equivalence in this class where you have cyclic modules. So it's a very interesting direction of research. There is also causal discovery from time series data. Of course, I told you, time doesn't allow you to have causal direction, as we saw in the XKCD comic, but it gives you something which is like the past. The present cannot cause the past, right? So the future cannot cause the past or the present. And this is used as background knowledge in these algorithms. And then they developed, this is a very important paper by Gerhardus and Jakob Honga. They publish, and they have now other papers in this direction. So another thing that is also very important is that before I told you how to do effect identification from a causal diagram. So recently so this is something that I'm very interested in. I'm researching on this direction. So how can I identify an effect without constructing the causal diagram, but using the peg, for example, the Markov equivalence class? So this is not new, right? So covariate adjustment, for example, was generalized for pegs, and we have the generalized adjustment criterion. So this is a paper by Perkovic in 2018. But recently, we proposed a complete calculus and algorithm for the identification of both marginal and conditional causal effects for any peg. So covariate adjustment is just the backdoor extension of, so you can identify if your effect is through adjustment, so through backdoor adjustment. But now we have the extension of the ID algorithm. So for any peg that you can have in the end, we can just use this algorithm and have the effect. We ask if the effect is identifiable or not, right? So this is a paper from 2022. So the classical pipeline that you saw in the beginning now can be extended by, instead of having a causal diagram here, the number 2, you have a peg, which you can learn in a fully data-driven way. So basically you need no knowledge, right? So you just run the FCI algorithm, you have a peg, and then you run this algorithm, that's the peg ID algorithm, or you can just start with the adjustment criterion, for example. But then if your peg, for example, is something more complicated, where your effect is not through adjustment, you could run this IDP or CIDP algorithms that we developed, and and ask if the solution is, or this probability of y given to x is identifiable or not. And then you can have like an expression like this, which is not adjustment, right? So it's a complete algorithm. You would just have the expression in a complete data-driven way. So this is also available as an R package. This is my GitHub. So you can basically download it and use it. And so what is identifiability from a PEG? So I told you what is identifiability from a causal diagram, but it's not that different, right? So identifiability is that now we are requiring that every causal model that's in this class has to have the same expression. So it doesn't matter what's the graph inside of this class, you have exactly the same expression, right? So you don't need to know what's the true causal diagram. You can work on the level of the PEG. Non-identifiability is when at least one of the models inside of this class has a different expression or is not identifiable. So here, for example, if you had the causal diagram, you could even identify the effect of X on Y, right? But you don't really know if you are under this other scenario where you have, for example, this bidirected edge between X and Y and makes the effect not identifiable, which is one of the models inside of this PEG here. So this uncertainty about what's the causal diagram, of course, is going to give you less power for identifiability, but sometimes you have identifiability in a complete data-driven way. So I want to finish with this overview of what is the causal inference workflow. We basically covered this part here, but we have many other tasks in the field. So here, basically, that is a continuous process, and it's really mimicking the scientific discovery process, right? Because we don't know the nature, but we can collect data from it. We can extract, we can use statistics in A here, statistical learning, to get some, to understand the constraints of the data. But we should incorporate knowledge. And this knowledge can come from experiments, can come from common sense, can come from different ways. But this constructs a different representation of our model. Doesn't need to be a causal diagram, can be a partial ancestral graph or even beyond the Markov equivalence class. And we answer questions from this object that represents our knowledge. So that's the power of the language of causality, is putting on a language that encodes everything that you know. And then once you have this very well encoded, we start asking questions. And sometimes these questions are not answerable. But we have, for example, causal experimental design that asks exactly the question, which answer I should have to improve in a way that in the next iteration of this loop, I improve my knowledge. And then this can be in a form of new knowledge or new data, right? So you should have like a continuous process where you, after doing these interventions, you cannot, you always have to look for interpretability of these models and understand how these interventions, how this knowledge that's being incorporated are changing the model and so on. And then you basically have this loop up to a point where we finally have our true model of reality. So there are many other topics in causality. I'm citing here just for you. There's like some references in the end. But these are just topics that I find very important in the field causal representational learning, which is related to causal abstraction. So what actually are variables? This is very special for natural language processing because words are not variables. We have like concepts, abstract concepts, and this is what's being learned through deep neural networks. But how can you make sure that these latent variables are preserving the causal relationships of our true underlying model? Reinforcement learning, we have many works on this field that not only applies reinforcement learning, but tries to recover causal effects, causal diagrams, and so on. Individual treatment effect estimation, data-driven covariate selection for adjustment. Like you don't need the causal diagram or even the PEG to see if your effect is estimated by backdoor adjustment. You can just have other techniques, partial effect identification, and so on. So you can take a look later. There's like many references here. I think I'm over time. So I would prefer to go to the questions. And also if you ask me questions through email, I'm happy to answer. Thank you. I think everyone's hungry. Okay, I'm going to be around here. So if you have questions and prefer to talk in person or even through email, I'd be happy to take them.
Thank you. Let's take the speaker again. And one small announcement is that after lunch, starting at 2 o'clock, this same room, there will be the panel discussion. So you don't want to miss that. Please be on time and enjoy lunch. Thanks.